Okay, so hello everyone. Welcome to One World Mathematical Physics seminar. So everyone, could you please mute yourself? And first of all, some announcement. In this seminar, you can always ask questions. You can ask questions during the talk, and you can either unmute yourself and ask, or you can use the chat box. Okay, so today we're very happy to have Robert Seiringer. And of course, Robert needs no introduction. He's very well known, for example, for his works on Bose-Einstein condensation, which are very extremely important, both from mathematical and physical points of view. And here on the back, you see the cover of his book with Elliot and Jan Philipp and Jakob about Bose-Einstein condensation. So today, I think Robert is going to tell us about Polaron. Okay, so please.
Thank you, Hal, for the introduction, and thanks to Daniel and Jan, not just for inviting me, but in particular for setting up this whole series of seminar for the initiative. I think this is really a great addition and very useful for the community. And I think we all appreciate very much the initiative. So thanks a lot. So today I want to talk about give a summary sort of about some new results of some relatively old problem, namely the one of the Fröhlich Polaron, and in particular the strong coupling limit. So let me just start with a picture explaining sort of the physics of the model, so to say, what we have in mind when we talk about the Polaron. So this is basically the interaction of one particle. Think of an electron, a charged particle that moves through a medium, and this medium can be polarized by the presence of this charged particle. Right, so here's sort of a rough picture that we have a medium. We think of it as a continuous medium, but of course, if you look very closely, it consists of some atoms, molecules. These are all neutral, but the presence of the charge can sort of polarize them, right? So you have little dipoles. So you have a local dipole moment that is created by the presence of this electron, and this dipole moment, of course, itself, I mean, it creates an electric field that interacts back on the electron. So you have a system consisting of one particle and sort of a continuum, a polarization field that's created by this particle. And if you treat this in a quantum mechanical way, then of course this polarization field itself is a quantum field of phonons, which the electron interacts with. Okay, so this is the basic picture behind it. We will study this Folic model, which is sometimes called the Large Polaron. So there you take already sort of a limit of large wavelengths of electrons, so you don't see the crystal structure. You really think of a continuum model because the length scale over which sort of the electron is spread out is much larger than the lattice spacing, so you already make a continuum approximation. Okay, so this basically leads to what is called the Fröhlich model. So let me very briefly just explain the definition, right? So the Hilbert space naturally is just an L2 space for the electron and the Fock space, a bosonic Fock space for the phonon modes, right? And so the Fröhlich Hamiltonian has naturally three terms. I mean, one is just the kinetic energy of a free electron. So that's the Laplacian in suitable units. The field energy of the polarization field is actually just the number operator on Fock space, simply because basically every point in space is just an independent harmonic oscillator, right? That's the dipole moment that can sort of oscillate there, the polarization field. So they don't talk to each other. There's no propagation. So the field energy is just the number of excitations of this phonon mode. And then you have, of course, a coupling term between these two. There's one parameter measuring the strength of the coupling, usually denoted by square root of alpha. And then you have the usual sort of linear coupling creating phonons due to the presence of the electron. There's this form factor, the 1/k here. This is physically determined simply by the fact that we're talking about an interaction of a charge, namely a monopole, with a dipole, right? The A measures the strength of the polarization field, and this is just the interaction of a monopole with a dipole, which decays like 1/distance squared. So in momentum space, it's a 1/k, right? So the physics determines simply all the factors here. The only free parameter is, so to say, the coupling constant, which you should think of as a material parameter. Really, it measures in some sense the polarizability of the medium, and it's just some material constant, okay, which could be small or which could be large in practice. Now, when we look at this model, we will actually be interested in the case of large alpha. So we sort of have a simple non-relativistic quantum field theory that we want to study sort of in a very non-perturbative, namely strong coupling limit. Okay, I didn't mention, but it's sort of understood from the notation, right? So the A and A dagger, they are the usual creation annihilation operators for the phonon modes, satisfying the canonical commutation relation. And I already said this is the model of the large polaron, where the field, the medium is simply approximated as a whole continuum. Okay. So minor technical note, maybe, I mean, the operator as it stands, it's a bit of a formal object, because this operator creating here a wave function, a phonon wave function with magnitude 1/k. This is of course not an L2 function, so it's not a priori obvious what the domain of this operator is, but you can just think of it, for instance, in a quadratic form sense and convince yourself it's closed and bounded from below, and therefore there's a natural self-adjoint operator corresponding to it, even though figuring out what its domain is actually requires some work, but this will not be relevant for us here. Okay, and the model itself is of course just sort of an example of many models of this kind, a small system coupled linearly to some quantum field, right? Another example of this kind would be the Nelson model as sort of a caricature model of electrodynamics. There's been boson models and other kind of toy models in quantum field theory. The Fröhlich model is just sort of one of them, but one that has a very special feature, namely sort of it becoming simpler at large coupling. And this actually can be easily understood or explained by a suitable change of variables, which I call the strong coupling units here. So you can sort of think, you just do this rescaling. So if alpha is large, sort of the electron will localize on a smaller and smaller length scales. Actually 1/alpha is the relevant length scale. So you just rescale all lengths by 1/alpha. And if you do the appropriate rescaling of the field operators, you find that in these new variables, the Hamiltonian up to a trivial alpha squared prefactor, which I can just divide for simplicity, looks like something that doesn't depend on alpha, right? Here's the same Fröhlich Hamiltonian again. The alpha has just disappeared after this rescaling, but it's of course still there. And where it is in the commutation relations. So these new field operators that are defined this way, they don't satisfy the canonical commutation relation with a factor 1 here. They satisfy them with a factor alpha to the -2. So you can actually think of this alpha coupling constant in the Fröhlich model, or rather alpha to the -2, as an effective Planck's constant for the quantum field. And of course, then from that, it's very natural to think of alpha to infinity as basically being a classical limit where this quantum field becomes a classical field, right? So that's naturally what is expected. If alpha goes to infinity, you should get sort of the same model where the A's, however, have become simply functions instead of operators. Okay, so this is called the Pekka approximation, or the resulting expression is the Pekka functional. So let's write it out. So let's just replace the A's by functions, maybe call them Z, right? The Z number substitution. And actually, it will be convenient to write things in terms of Fourier transforms. So the Fourier transform of Z, I call phi here. So phi is still here a complex valued field. And if we now just plug this in, we obtain what is called the Pekka functional. So more precisely, what I do is I replace the operators by the functions, and then I take the expectation value in some wave function of the electron. That's the psi. Right? The electron is sort of the only quantum degree of freedom left. The rest has now become a classical field, which we call phi. So the field energy, of course, is now just integral phi squared. And the interaction here, you see explicitly, since we took a Fourier transform, the interaction of the charge psi squared with the polarization field, which is really the real part of this complex valued field phi. Its imaginary part somehow being the canonical conjugate variable. And this real part of the field interacts via sort of a dipole interaction, right? 1/x minus y squared with the charge. So this is sort of the classical analog of the Folic model, and let's call it the Pekka Functional. It depends on two complex functions, complex valued functions, psi and phi. If we're, for instance, interested in the ground state energy, so if we want to minimize energies, then of course the minimization with respect to phi is sort of trivial, right? Because it's a quadratic function in phi. So we can, of course, explicitly do the minimization in phi. Sorry, forget about the pi. That's from some old version of the slides. That should not be there. If you minimize over phi, we just complete the square, and you see you get sort of a convolution of 1 over x squared with itself, which is nothing but 1 over x. So what you end up with is what is also called the Pekka Functional. So it's just you have an effective self-attraction of this charge, right, with density psi squared with itself, an instantaneous one with a Coulomb kernel, right? So this is still psi is still sort of a free parameter, the electron wave function, and you see the effect of the field after you've integrated out the field in the sense of minimizing over the classical field variables. You get an effective self-attraction between the electron, right? Mediated sort of by these phonons of the classical polarization field. Now, if we look at this sort of purely as a mathematical object, right, we would now, of course, also like to minimize over psi, say, right? And then sort of the interesting question comes up about the existence and uniqueness of minimizers of this problem. So this was something that Elliott Lieb actually studied back in the 70s. So he proved that there exists a minimizer of this problem, right? And not only that, actually the hard part is to prove that it's unique up to, of course, the trivial symmetries of the problem, which is on the one hand, the sort of U1 phase factor of psi, and more importantly, the translation invariance, right? The whole model is, of course, translation invariant. So also this resulting functional is translation invariant, yet there exists a minimizer. And of course, there's a whole family of minimizers respecting these symmetries. However, there are no other minimizers. So the minimizers are unique up to symmetries, which is actually far from obvious in sort of an intricate analysis using in particular Newton's theorem and the sort of nature of the Coulomb interaction. So an analogous problem, analogous question, as far as I know, is still open if you replace the power 1 here by any other power, where you would probably expect the same result, but it's not known. Just the very fact that the minimizer exists, this is sometimes called self-trapping in physics, right? It's sort of a result, of course, of the classical approximation. I mean, the quantum model will never have a minimizer, right? You have translation invariance, so you have purely continuous spectrum based on that. But the classical approximation sort of has a minimizer. The electron sort of sits in the potential well, it creates itself, so to say, in the polarization field. Now, another topic I want to talk about here is dynamics. So there's also, of course, a natural dynamics for this classical approximation. These are called the Landau Pekar equations. And it's just thinking of this as a dynamical system, right? So basically psi and psi conjugate and phi complex conjugate, or if you want equivalently, the real part and the imaginary parts of psi and phi, they are canonical conjugate variables. So you just write down Hamilton's equations for this Hamiltonian, and those are the Landau Pekar equations. Actually, alpha reappears. You see, the classical model, of course, has no alpha in there, right? The alpha disappeared. That was an effective Planck's constant. But if you do dynamics, you have to keep in mind that the commutator of the field variables had this alpha to the -2, which now in the dynamical setting, you should multiply the Poisson bracket with. So in other words, the time derivative of the field variable actually naturally has this alpha squared in front. The time derivative of the quantum of the electron wave function psi does not, right? So the Landau Pekar equations still have the alpha in there, right? Here it sits. And since this should be sort of a good description of the system for large alpha, you see that there's sort of an interesting limit sort of already involved on the classical level of the equations, namely an adiabatic limit. Namely, the psi and the phi, they sort of live on different length scales, right? The natural length scale on which the field varies is a very long length scale, time of order alpha squared, whereas the electron evolves in times of order 1, right? So the field is sort of a very slow variable as compared to the electron. That sort of to lead some kind of adiabatic decoupling, which is sort of already on the classical level. And this is actually what will make the analysis quite intricate. I mean, the analysis of trying to connect those equations with the actual Fröhlich dynamics, right? Namely the quantum problem, the time evolution generated by the Fröhlich Hamiltonian. But I'll come back to that. Okay, but let's maybe first talk, which is a bit easier, let's talk about the ground state energy, right? If one just wants to compare, say, the classical ground state energy, maybe the minimum of this Pekar energy with the one of the Fröhlich, then this is something that was done way back. So here, let me introduce the notation. So let's call EP the classical energy, right? So the minimum of this, Pekar energy functional here, which is some number, one can at least numerically compute. So this is, of course, based on what I explained. I guess it's not a surprise that you expect that this number to be asymptotically correct for large alpha. So the precise statement is, if you look at the ground state energy of the Fröhlich Hamiltonian, and this H alpha, right, just meant that the trivial alpha squared prefactor I took out, I divided by alpha squared, then actually in the limit, the ground state energy is equal to the classical approximation. This was actually proved by Donsker and Varadan in the early 80s using sort of Feynman's description of the problem, namely the fact that there's a path integral formulation of this problem that was discovered by Feynman. Basically, if you write out the heat kernel for the problem, since the field appears quadratically, if you introduce a path integral formulation of the electron, you can integrate out the field and just effectively get sort of an effective measure for just the electron, which is sort of this what we normalized Wiener measure. I mean, you have the Wiener measure just coming from the Laplacian, right, just the Brownian motion. And then from the integration out of the field, you get an effective self-attraction of this path, right? So you see this is just a multiplier here for a given path, omega, which is some closed path of length t, say. You have an effective self-interaction of the path that's retarded, right? So the path at time t interacts with itself at time t plus s with a Coulomb interaction, and s is some number order 1, so there's this exponential weight here where you integrate over the retardation s, right? And alpha appears as a coupling constant. And what Donsker and Varadan actually did is study this measure, or more precisely just sort of the partition function. So you do this integral. This integral will be asymptotically for large t equal to the ground state energy, or whatever, its logarithm divided by t will be the ground state energy. So you have to sort of send t to infinity and then study what happens for alpha to infinity. And that's sort of what they did with their sort of large deviation machinery. This is just as a side remark. I will not make use of this anymore. Later, this result was reproved and actually strengthened by given explicit error bounds by Lieb and Thomas in, I think, well, it depends on your background, but from my perspective, using much simpler techniques, sort of operator techniques to obtain explicit bounds on the ground state energy of the Fröhlich Hamiltonian in terms of the Pekar energy. Actually, the upper bound is easy. You can always make the quantum field classical by just a coherent state ansatz. So this is what we've written here. Sort of if you make the ansatz that your wave function is just the tensor product of a wave function for the electron times a function for the field. And this function for the field will naturally be a coherent state. That's what this notation suggests. So W is just the usual while operator and omega is the vacuum. So W applied to the vacuum will give you a coherent state. And that, I mean, you have to put in the appropriate alpha factors here. Then this will turn the quantum field into a classical field, and you can minimize over psi and phi, and you get the sort of Pekka minimizes out, and then you get exactly the classical number. So the classical number is always an upper bound to the quantum ground state energy. But what Lieb and Thomas proved is actually you get a lower bound in terms of the same quantity up to errors that are suitably small. In fact, the error bound they got was sort of alpha to some power minus 1/5. Okay. So what I'm concerned with here is actually the leading order correction. So what is truly the correction term, sort of the quantum correction to the ground state energy in this classical limit. And this you can sort of think of as quantum fluctuations, right? So the quantum field to leading order is sort of its classical field, but of course, since it's quantum, it had a sort of 0-point fluctuations around the classical value, and those should determine the leading order corrections. And to see, sort of to motivate the formula for them, you can argue as follows. If you start with the classical functional, let's not actually minimize over phi, let's minimize over psi. Actually, because psi are the fast variables after all, this is sort of, again, this adiabatic picture that given phi, psi will always just want to sit in the potential well created by phi. Right? So if you think back at the classical functional, it was of course quadratic in psi. So for a given phi, minimizing over psi just means you take the ground state energy of the resulting effective Hamiltonian for the electron, which is just the Laplacian, and the potential created by the polarization field, which is the field convolved with 1 over x squared. That's sort of this monopole dipole interaction. So that's the effective Hamiltonian for the psi. So minimizing over psi would mean take this ground state energy, right? The integral phi squared is still there. It's unaffected. Right? So this is now sort of still a Pekka functional, but as a function of phi. And now if we expand this, well, first of all, if we minimize, of course, we again find just the Pekka energy, but now let's expand this to quadratic order around the minimizer, right? There's one can use Lieb's results to also see that this functional has a unique minimizer up to translations, of course. So let's pick one of the minimizers and let's expand to quadratic order around the minimizer. So this leads to the Hessian, which you have an explicit expression for, because I mean, the second derivative of this term is of course trivial, it's just the identity. And here you can just do second order perturbation theory, right, to get the second derivative. So you have sort of an explicit expression for this Hessian. Okay, and then of course there are higher order terms, but if we forget the higher order terms and if we just make a quadratic approximation, but now reintroduce the field variables. Oh, sorry, I should give some credit here and mention two things, I mean, about this Hessian. So one is, of course, the Hessian is positive, clearly, because we expand around the minimum. The Hessian is also less than 1. That follows from the fact that, I mean, the 1 comes from here, but here the second derivative is negative, right? Because this infimum of the spectrum is clearly a concave function of phi. So it's between 0 and 1. And actually, Enno Lenzmann has proved that it has exactly 3 zero modes, right? Naturally, it will have 3 zero modes just from the translation invariance, right? The fact that there's a whole manifold of minimizers. If you follow this manifold, the energy stays at the minimum. So there must be 3 zero modes, but Enno actually proved that these are there are only these 3 zero modes. So this is sort of a strengthening in some sense of Elliott Lieb's results on uniqueness. He also proved that there's sort of a strictly positive second derivative at the minimum, modulo, of course, the symmetries. Anyway, this was just a side remark. Now, but if we take this seriously and now sort of just do the quadratic approximation, but now reintroduce the quantumness, namely really think of the field as a quantum field, right? Then we have a system of harmonic oscillators if we ignore anything else that's quadratic. And for harmonic oscillators, we can compute the ground state energy. Right? From the commutator, the field variables, we get the 1 over alpha squared. So the natural conjecture would be that the leading order correction to the classical approximation should first of all be order 1 over alpha squared compared to the main term, and it should be given by the ground state energy of these infinitely many harmonic oscillators sort of described by this quantum field, right? And if you do the calculation, right, here you should think of this as a frequency squared, right? If you think of this as a frequency squared, the ground state energy is the frequency, so you have to take a square root. So you naturally would get the trace of the square root of this h. Okay, now this is infinite, but there are other infinities in the problem, and that's why you should subtract this 1. This is sort of the infinity that comes from the fact that the field energy, right, was really A dagger A. We had already subtracted the 0 point energy, right? And that's sort of this subtraction here, which is of course infinite because there are infinitely many modes, but so is this guy infinite because it turns out that H, this Hessian is actually just a trace class perturbation of the identity. So in other words, this expression is actually trace class. Okay, so this prediction makes perfect sense, but to arrive at it, you have to sort of, in good faith, ignore a few infinities or really subtract a few infinities and hope that they cancel out. This is the main reason why this is still a conjecture and not a theorem. Why is it difficult? It comes exactly from these infinities, or more precisely from the infinite dimensionality. And you can also see it up here in this classical picture, right? I ignore terms higher order. So this sort of means that the classical field here, sorry, the quantum field has to somehow be close to the classical field. But actually, this term is never even finite. You see, for any, basically for any function in the domain of the Hamiltonian, this L2 norm difference is always infinite. Because just because there are infinitely many modes. I mean, you have to just think of, you have an infinite product of oscillators. In all directions, you can be close to the minimum. But if you have infinitely many directions and those you add up when you compute the L2 norm, then of course the L2 norm is never finite. So not only, I mean, phi is never in L2. It's never in L2 close to the minimum, strictly speaking. So the only way to sort of make this rigorous is to somehow effectively reduce these infinitely many directions to only finitely many relevant ones. And to get to finite dimensions, you sort of have to solve an ultraviolet and an infrared problem. I mean, basically, if you do both an ultraviolet and an infrared cutoff, then of course you reduce the problem to finitely many modes. And basically what I want to just mention, because I don't have time to explain in detail, is that we can solve the ultraviolet problem, but not the infrared problem. So in other words, if we make an infrared cutoff in the sense that we put the whole system into a finite volume, say, right, then there is no infrared problem. Let's make a finite volume cutoff and let's take otherwise the exact same model. Then we can actually prove this theorem. And this is sort of briefly explained here on my next slide. So this concerns a model. I have not actually bothered to write down the definition, but it's sort of contained here. We call it the confined Polaron. So just imagine that everywhere you saw R3 from before, replace it by some omega. Okay, and let's think of omega being some nice, compact and smooth set. So that means both the electron, right, is just confined to some finite volume, say Dirichlet boundary conditions, but also the field. And wherever you see some kernel like 1 over x minus y to the minus 2 in this case, just think of this as the appropriate expression as a function of the corresponding Dirichlet Laplacian. So 1 over x squared just becomes, so this should be xy. This is the integral kernel of, say, 1 over square root of the Laplacian, right? Which is exactly right if omega is R3. Right, so then this is just 1 over k in k space, so it's 1 over square root of the Laplacian. But let's just make the replacement for some omega like this, right? So this defines now a confined Polaron model, and for those for this particular model, we have proved exactly this conjecture that I just mentioned. So this is joint work with Rupert Frank. So we prove this two-term asymptotics here, that if you look at the ground state energy of the corresponding Fröhlich model, which of course now depends on this particular choice of omega, it's equal to its Pekka approximation, which of course also depends on omega. And as a leading order correction, we can identify these quantum fluctuations, which is exactly the trace, as I tried to explain, of the square root of the corresponding Hessian of the classical functional minus the identity. Again, it's this difference that is actually trace class. So this trace makes perfect sense, and it identifies sort of the corrections due to the quantum fluctuations, plus higher order terms for which we have some bounds. I should say that this theorem sort of works really sort of because for a bounded domain, the Pekka functional will generically have a unique minimizer, right? We're not breaking the translation symmetry by hand. And generically, if you take some domain, this will mean you have a unique minimizer up to, of course, the trivial phase symmetry. Now, this is not really proved, actually, we can prove it for a ball. In fact, together with my student Dario Feligiangeli, we have proved for a ball that indeed the classical Pekka functional has a unique minimizer. For this work with Rupert here, it was just important that this is the case. So we just use this as a working assumption, so to say. We said, let's pick an omega where we have a unique Pekka minimizer, and then we can do actually analysis of the quantum problem and indeed identify a two-term asymptotics. Very recently, and this is actually still in preparation, although it should be in the archive in the next few days, in joint work with Dario, we have actually proved the same statement for omega a torus, I mean a flat torus. So in other words, if you think in momentum space, you have now discrete momenta instead of an integral, right? So this has the additional complication, of course, that you still have translation invariance and you still have a whole manifold of classical minimizers around which you have to expand. You still have the zero modes of the Hessians, which complicates things. So this was actually quite a lot of work to get this to work in the torus. Of course, the motivation for studying the torus is that you're sort of one step closer really to the full space problem. So we've sort of solved the problems that come from translation invariance to be able to show this also on the torus, but we still haven't solved the problem that comes sort of from the lack of compactness in infinite space. That's why on R3, this corresponding statement is still a conjecture, not a theorem.
Robert, so does this error term depends on the volume or something?
Yes,
like
yes.
that?
So this, of course, this little O will also depend on omega. Everything depends on omega.
Okay, so that kills you if
yes,
omega is large.
Exactly.
Okay.
That's exactly the point. Yes, I should have probably indicated this in the notation. This depends on the volume and would explode if we let the volume go to infinity. So we cannot sort of obtain the R3 limit in this way. Exactly. Okay, so let me maybe to sort of then could connect to my second main topics, which is the dynamics. Let me actually point out that this energy, I mean, this is basically related to what I said already. I mean, this is the ground state energy of a system of infinitely many harmonic oscillators, right? In fact, that means it's the ground state energy of a quadratic Hamiltonian. You can think of it as a Bogoliubov type Hamiltonian, right? It's a quadratic Hamiltonian on Fock space. And in fact, what is this quadratic Hamiltonian? It's sort of the fluctuation Hamiltonian, if you want. And this is just the second quantization of the Hessian of this classical Pekka functional. Okay, so the Hessian has two terms, right? It has the identity, whose second quantization is just the number operator, right? And then there's the term coming from second perturbation theory, right? So what you have to do for second perturbation theory is I'm going to take the ground state, right? You have to multiply by the perturbation, divide by the resolvent, and so take the corresponding quadratic expression. That's what is written here, or more precisely already, it's second quantization. So let me explain the notation. Maybe I start at the end, right? So if you think in terms of the classical problem, right? We saw that the electron is always in the ground state of the corresponding sort of Schrodinger operator, right? Which is the Laplacian plus the potential generated by the field. Okay. So so actually I want to define this not just at the minimum, but actually for any phi. So let's pick a phi, a field, such that this one particle Schrodinger operator has a ground state below its essential spectrum, right, which starts at 0 because this is a potential that vanishes at infinity. Okay, so this is some L2 function convolved with 1 over x squared. So let's assume this has a ground state, and this ground state I call psi sub phi, right, because it's indexed by this field phi. It depends on phi. Okay. So the ground state energy I will call E phi. So I assume that this is a negative number, right? So that's exactly the assumption that the field is such that this potential sort of creates a bound state. Okay. And then I can look at this reduced resolvent. So I can take it the resolvent of this Hamiltonian H, right, minus its ground state energy. If I project away from its unique ground state, then this inverse exists, right? So this is what I mean by the reduced resolvent, right? So you look at the subspace orthogonal to the ground state, in which case you can invert H minus E, right? So that's what I call R. And again, it's indexed by phi, right? So phi is sort of the is a variable for the field. Okay, and so given phi, I can now define a quadratic operator as it's defined here, right? So phi is a linear expression. So this is the field operator here, phi of f, and you evaluate it at a v that depends on x. Right, so this is my notation v sub dot. So this is vx of y. So this is the x is a parameter, and this is a one particle wave function. So to say that's created by this field phi. X is a parameter over which I integrate. Namely, I take the expectation value in this one particle wave function psi. Here is the resolvent, and so this is sort of x is being integrated over. Right, so this is a quadratic operator in the Fock space for a given value of this function phi, right? And now I can connect back to what I said. If you look at the minimum, so if you take phi to be the Pekar minimizer, then this is nothing but the second quantization of the Hessian of the Pekar functional at the minimum, or more precisely, this is the second quantization, because there's the identity, and then there is from the second derivative of the ground state energy, you get this expression. Okay, so that's sort of the fluctuation Hamiltonian. If you compute its ground state energy, that's exactly what you get. Okay, that's effectively where the quantum corrections come from. Okay, but now I will need this operator more generally, not just at the minimum, but for a general function phi. Okay, that's why I defined it here in general, because I needed to state our main result concerning the dynamics. And this is a joint work with Nikolai Leopold, David Majtruskas, Simone Rademacher, and Benjamin Schlein, where we sort of prove the validity of the Landau Pekar equations in a suitable sense. And let me try to sort of explain here the main result. And that's the following. So we start with an initial state that's a classical one, or more precisely as classical as it gets, right? So the most classical states you can write down is you take a product state, sort of unentangled, right? The electron is in some state psi, and the field is a coherent state. Sort of, you can think of this as a Gaussian function, right? The minimum uncertainty state around its classical value, alpha squared phi naught. Okay, so we take some phi naught, and let me pick a phi naught that creates a bound state of the corresponding Hamiltonian for the electron. So that in my notation means that the E phi naught is negative, right? So the corresponding psi phi naught exists, right? That's the ground state of this one particle Schrodinger Hamiltonian I had just written down. So in other words, we think of initially we put the field in some state, right? It doesn't have to be a Pekar minimizer. Take any classical state, but put the electron in the corresponding ground state that's sort of created by this potential well. So this is sort of this adiabatic picture that somehow the field moves very slowly, the electron moves very fast, so we better trap it. We put it in the ground state of the corresponding sort of very slowly varying Hamiltonian. That's sort of the picture behind it. But a priori, this is just an initial state. Coherent state times electron, but a very specific electron function, namely one that's actually sort of the ground state of the corresponding Hamiltonian based on sort of this classical picture of the potential well. And now let's do the dynamics, right? So now we apply the actual Fröhlich Hamiltonian. Now we apply the Fröhlich Hamiltonian, right? H alpha again is sort of 1 over alpha squared times the Fröhlich Hamiltonian. So therefore, what we would really like to do is we would like to follow its time evolution for times of order alpha squared, right? Because this is where the classical Landau Pekar equations really show non-trivial variations. Okay, and our statement is that actually we can follow this time evolution. We still find the tensor product. So at a later time, and by time I mean times of order alpha squared, the electron just is in the time evolved state following the Landau Pekar equation and the field, right? So both the field and the electron solve the Landau Pekar equations, of course, with the same initial conditions. There's a trivial phase factor, which I don't care about, right? That's why I didn't explicitly write it down, but there's, of course, an explicit expression for it. But to make this work sort of as an L2 closeness, right? So there's a norm difference here, and the difference is small if alpha is large. There's some universal constant over alpha. But actually to make this work, you cannot keep the vacuum a vacuum here. You actually have to evolve the vacuum according to the fluctuation Hamiltonian. So this is what is written here. Here, omega actually depends on time. It's initially the vacuum, but then actually you create excitations because you follow here the Schrodinger equation, a time-dependent Schrodinger equation according to this it's a quadratic evolution, a time-dependent one with sort of the fluctuation Hamiltonian generating the time evolution. Okay, this is sort of an alpha independent quantity. So the picture is this evolution will not create many excitations. This will sort of only create order 1 excitations, whereas this guy has sort of alpha squared excitation. So this is really just a small correction to the classical. This is sort of the quantum correction, if you want, to the classical picture, but it's necessary if you really want an L2 convergence of the wave function. So if you really want to compare the wave function, which is sort of a function of many, many variables, right? Lots and lots of excitations. It's a coherent state with many excitations. If you really want to follow it on an L2 level on the full Hilbert space, you have to actually take these quantum fluctuations into account via this fluctuation dynamics. Otherwise, such a statement simply cannot hold. If you're willing to look only at less information, for instance, at reduced density matrices, then actually you don't need to talk about the quantum fluctuations. So as an example, if you don't look at the full time evolved wave function, but say look at the projection onto this wave function and trace away the field, just look at the electron part, then the statement, it's an immediate consequence of this theorem, basically, is the statement is you will just find the time evolved electron, evolved according to the Landau Pekar equations. And similarly for the field, if you look at the natural reduced density matrices, say the expectation of A dagger A, then you will also simply see the classical evolution phi. You don't see the quantum fluctuations, so to say. So if you look at reduced density matrices, you don't have to talk about quantum fluctuations, but actually if you want a full approximation on the L2 level, so to say, of the full wave function, you need to take these quantum fluctuations into account. Interestingly, however, I think we do not know how to prove these weaker statements directly without actually first proving the stronger statement involving the quantum fluctuations. To prove sort of directly the validity of the Landau Pekar equations, sort of just on the level of reduced density matrices. Let me comment maybe once more on the special initial conditions, right? As I emphasized, it's not just a classical state, it's a very particular one where the electron is sort of at the instantaneous ground state of the sort of Schrodinger operator with potential created by the classical field. Right? And this is sort of reflects the adiabatic nature of the Landau Pekar equations for large alpha. Right? As I said, there is sort of this separation of timescales. The polarization field moves very slowly on the timescale of order alpha squared. The natural timescale of the electron is, however, order 1. So if you don't sort of trap it initially, after times of order 1, it's just gone. Right? And you don't see it anymore. So to make sure that it actually stays, you have to sort of trap it. So you put it in the ground state. And then you're exactly in the adiabatic setting where you have a potential, you have a system in its ground state, but the potential moves very slowly, right, on time scale of order alpha squared. And of course, according to the adiabatic theorem, the psi will just stay in the instantaneous ground state. It just follows the ground state, right? And this is actually something that we also prove. It's a sort of a non-trivial extension of the usual adiabatic theorem because these are fully nonlinear equations, but one can still prove the adiabatic theorem, and it's actually an essential ingredient for the proof of our main result here, that basically you could replace this psi t here also by the psi sub phi sub t, meaning it's not really the time evolved psi, it's just the instantaneous ground state, but actually the two of them are very close. That's sort of the adiabatic theorem, which we actually also use and need for the proof of this main result here. Okay, so then that leaves me with the last topic. So this is yet another result, another recent result on the Fröhlich Hamiltonian in the large coupling limit, and this concerns its effective mass. Let's just shift back actually to the original variables, which is a somewhat simpler. So I have not done the rescaling of the variables with alpha here. I mean, I could, of course, it makes no difference, but it's maybe slightly more transparent this way. So what is the effective mass, right? So the Folic model is, of course, translation invariant. So on the quantum level here, that means in particular that the Fröhlich Hamiltonian commutes with the total momentum of the system, or more precisely, all the three components of the total momentum, right? And the total momentum is, of course, just the electron momentum, so minus I times the gradient as usual, and the field momentum, which is just the integral of k times A dagger k ak, right? Because this counts the number of phonons with momentum k, and if you add them all up for all k, right, you get the total momentum of the system. Okay, so this is a conserved quantity, and as usual, if you have a conserved quantity, right, you can diagonalize the Hamiltonian, so to say, and these conserved quantities simultaneously. Since here we have continuous spectrum, that means that sort of there's integrals instead of sums. So formally, you could say that the Hamiltonian has a fiber integral decomposition of this kind. Sorry, I cannot mark this here for some reason, but you can think of this Hamiltonian as being an integral of the Hamiltonian, so to say, that you get by fixing the total momentum P to have a definite value. Right? You can get rid of one, or more precisely 3 degrees of freedom, right, simply by fixing the total momentum. So then effectively you work on a Hilbert space with 3 degrees of freedom less, and it's convenient actually to choose as these 3 degrees of freedom the electron degrees of freedom. So there's a certain unitary transformation involved, known as the Lie-Low-Pines transformation. In any case, you have an explicit formula for this HP, right, fixing the momentum P, and it's sort of the natural thing you would get if instead of the electron momentum, you simply substitute the total momentum minus the field momentum, which is after all what it is. So where before we had a Laplacian, right, an electron momentum squared, we actually now have the total momentum, which is a number, right, or it's a C number, it's just a fixed number, fixed 3 numbers, P, minus the field momentum squared. Everything else is the same in the Fröhlich Hamiltonian, except there's no more x in the picture, right? Where there was an e to the ikx before, it's just 1, so the x is out. It's like effectively you've set x equal to 0, there's no more x, and you've replaced the electron momentum by the total momentum, which is not just a number, minus the field momentum. Okay, and then you get sort of this Fröhlich Hamiltonian in the fiber total momentum being p, and it's now just an operator on the Fock space because we've used sort of the translation variance to get rid of the electron degrees of freedom in this sense, right? The price we had to pay, of course, is that this is now not a quadratic operator in the field modes anymore, right? Here you have the field momentum, which you have to square again. So this is a quartic operator in the A's and A dagger. So that's sort of effectively where the interaction is sort of hidden, and that what makes this thing not trivial. Still, just for the definition of the effective mass, you basically just look at the ground state energy as a function of P, right? So each of these HPs will have a ground state energy. Let's call it E of P. And the effective mass is simply defined by expanding this for small p, right? And basically looking at this P squared term. So you basically say for a particle of mass M, you would expect that the energy goes like P squared over twice the mass, right? That's just the non-relativistic formula for the kinetic energy. So we use this as a definition. So formally, right, you take E of P minus E of 0. This should go like P squared. So let's divide by P squared and let's take P to 0. And we call the result 1 over twice the mass. Now, so of course, if you had just a free particle, this mass would actually be 1/2, right? Because that's how we chose our units. I mean, the Hamiltonian was just the Laplacian, so the 1 over 2m in front was 1, so the bare mass, so to say, is 1/2, and it's not difficult to see that it sort of can only increase due to the interaction of the field, right? So physically, what is happening is that somehow the electron gets stressed with all these excitations from the polarization field, and effectively becomes heavier, right? The sort of inertia goes up. And therefore we expect this number m to be actually larger than 1/2. In fact, you expect that in the classical limit, where sort of the electron becomes heavier and heavier, it should even diverge, right? And there's a concrete prediction, which is sort of at least loosely based on the Pekar approximation, that suggests a concrete formula. I have it actually displayed on my next slide, a concrete formula for this effective mass. But maybe more important than the formula is even the fact that it's supposed to grow very fast. The formula suggests it grows like alpha to the fourth as alpha goes to infinity. So this has somehow been a long-standing open problem, and it's still as open, of course, as it always was. But we've recently made some small sort of contribution with Elliott last year. We could actually at least prove that this mass diverges, which was not even known, right? So there were no quantitative bounds on this effective mass. We could at least give a bound, a very weak one, but still that show that indeed the effective mass diverges in the classical limit, as it should be, because you expect sort of in the classical limit this kind of self-trapping to happen. And self-trapping is yet another way of saying that the effective mass is infinite, because only then you can sort of create a wave packet that has a definite location, so to say, an L2 function with energy that is sort of equal to its ground state energy, right? So if this function E of P were exactly flat, then you could use this little momentum window to actually create a wave packet that has sort of sits somewhere, right? And this would be the self-trapping. So the flatness is exactly related to the mass being infinite. It's of course always finite, but in the limit, it actually diverges. And this is what we managed to prove. So these were basically the results I wanted to explain. Maybe a bit faster than I expected, but let me just maybe use a couple more minutes to just summarize, maybe to just remind you of what I told you, and maybe also mention these open problems, some of which I've already mentioned anyway during the talk. So the main results were we could actually prove sort of the quantum corrections to the ground state energy of the Fröhlich model at large coupling, sort of beyond the classical energy that you get to leading order. There's sort of these quantum corrections coming from fluctuations. And even though the general problem is still open, we could prove it sort of in the confined case where the model is defined only in finite volume, be either sort of a nice domain or a flat torus. We've also proved the validity of the Landau Pekar equations as sort of a classical approximation to the Schrodinger dynamics generated by the Fröhlich Hamiltonian. This was for very specific initial conditions that actually reflect sort of the adiabatic nature of these classical equations for large alpha. And it was actually important, and that's sort of the connection between the two, that we actually needed sort of the fluctuation Hamiltonian to actually derive this result. So in some sense, we are not able to show the validity of the leading order term in some sense without looking also at the corrections. So the quantum corrections sort of allow us to prove the validity of the classical equations. This having to do, of course, with sort of the particular topology, if you want, namely the fact that we worked with the actual L2 norms of the wave functions that required to work to such an accuracy to also see the fluctuation terms. And finally, the last topic I briefly mentioned was that we can now prove the effective mass of the polaron to actually diverge to infinity in the strong coupling limit. The natural open problems are, of course, the ones I mentioned, right? So we expect that this quantum corrections to the ground state energy should also hold in the unconfined case. It's mainly a technical problems, I think, that keeps us from proving them, but they don't seem to be, it doesn't seem to be an obvious route towards solving them. So this remains open. Here is the formula I mentioned for the effective mass that you can sort of argue follows from the Landau Pekar equations, although only with a little leap of faith. And the prediction would be this alpha to the fourth, as I said, but times actually an explicit constant, which is basically up to some pi's, the 4 norm of the minimizer of the Pekka function. Purely on the classical level, actually, there are some interesting open problems. I think I'm not aware of any study, for instance, of long time behavior of these Landau Pekar equations. I think there's some interesting questions. we, for instance, looked at the question of existence of traveling wave solutions, which we don't expect to exist at all, but also that is widely open. So I think there are sort of lots of interesting questions on this sort of very old problem, but I think there's still lots of work to be done. So thanks for your attention, and I'll be happy to try to answer questions if there are any.
Well, thank you, Robert. This was very, very clear. Okay, so any questions or comments from anybody?
Okay, it's Michael Siegel.
Hi, Michael.
So I have a couple of questions. First of all, Robert, thanks for the great talk. Unfortunately, I missed the beginning of it. I have two questions. First of all, about the effective mass definition. So you assume that 0 is a critical point, 0 is a minimum of your function E of P, and
Yes.
that E of P is spherically symmetric.
Yes.
Otherwise, you would have to have an inverse Hessian here.
Yes, that's correct. So the spherical symmetry is a trivial consequence of the spherical symmetry of the model. So there's nothing to prove, I think. To prove that E of P is actually minimal and at 0 and that this limit exists actually requires some work. But this is fairly standard for this particular Fröhlich model because you see there's a gap. I mean, it's massive, right? So there's a 1 here. So that actually allows you to show that this E of P is actually an analytic function for small p, namely until you hit sort of the essential spectrum, which starts 1 above the ground state energy. So you have a little window where you have analyticity, so you can convince yourself that this limit actually always exists. I mean, a priori it could be 0, but that has also been proved that it's not. So in other words, the effective mass is not only well defined, it's also always finite. So all these things are actually known, and maybe the last one is a bit tricky, but the rest is actually easy to prove because of the structure of the model, basically because it's sort of the dispersion relation is massive that allows you to prove this quite easily.
Okay, my second question is a little bit more, is about the nonlinear adiabatic theory. So is it somehow can you use the results by Zhou, Gang, and Grech?
I don't know. We have not used them, so I have not really studied them. They have looked, I think, at something like a nonlinear Schrodinger equation, right? If I remember correctly. So here it's a bit different because you see the structure is a bit different. Here you have sort of 2 separate equations for the field and the electron, and the field sort of, it satisfies this kind of wave kind of equation with a source term given by psi, right? So actually, if you send alpha to 0, this would sort of correspond to a nonlinear Schrodinger equation, because then you would say instantaneously, phi is given here. You could plug in phi and you would get sort of an effective Coulomb kernel here. But here's sort of the opposite limit. So it's quite far away from NLS. So it's not clear to me that there's a direct connection. However, the techniques may well be connected. I mean, the techniques are now not, I mean, they're sort of adapted to the specific problem at hand, but I don't think they are fundamentally new or so. So I would not be surprised if there is some sort of conceptual overlap, but we have not sort of explored that directly, I would say.
Maybe can I also say something?
Yes,
I think that Gang Zhu and together with Rupert Frank applied those kind of techniques also to this Landau Pekar equation, and we have some result in 1 dimension. And so our technique will a little bit different for this adiabatic theory.
Yes, so I don't know if that work is sort of related to this other work by Gang that Michael mentioned, but it's true that there was an adiabatic theorem by Gang and Rupert on sort of a 1-dimensional analog of these equations, but it was very 1-dimensional in the sense that they had to, for instance, assume that there's a unique bound state of this effective Schrodinger operator, no resonances, whereas here we are always in a situation where we have infinitely many bound states, so it's quite a different setting, I think. So that suggests that there may not be direct link between these methods.
Any other questions or comments?
Can I ask a stupid question? What about the case of small alpha?
Yeah, so in the case of small alpha, of course, we shouldn't be talking about the classical model at all, because then, I mean, you can, of course, but there's no connection. Here, you basically can convince yourself that perturbation theory works in the sense that the energy as a function of alpha is actually an analytic function, and you can in principle compute it for small alpha to arbitrary order doing perturbation theory. Also, actually, the effective mass can be computed to, I don't know to how many orders it has been computed, but basically perturbation theory converges. So you would say that for small alpha, you can compute things using perturbation theory. Of course, how small alpha has to be and how high up you can go, I don't know, I haven't investigated. But basically, perturbation theory is not divergent anywhere. I think the quantities, both the ground state energy and probably even the effective mass, are analytic. The ground state, so to say, that exists in this fixed fiber of momentum zero is an analytic function of alpha. So in principle, perturbation theory converges, and you could compute things for small alpha.
Analytic with what radius?
That I do not know. I don't know whether anybody has explored that. You see, I guess the real question would be with what analyticity domain. I think this is certainly not known. What the radius would be at alpha equals 0, I do not know.
Another question, suppose you replace 1 over k by some nicer form factor. Is it still an interesting problem, or? So
then it depends a bit on whether you do this before you scale with alpha or after. You see, you lose the scale invariance. If you do it here on this level, where I've already sort of scale, alpha is already only contained here in the Planck's constant, I don't think it makes much of a difference. In fact, the more ultraviolet regular you make this, the easier it probably is. So it may actually save some work if you make this ultraviolet regular, for instance. But of course, if you do it in the original Hamiltonian, then the alpha scaling will not work. So then this will become alpha dependent somehow, and then it may not help at all. I mean, the whole setting is slightly different. I don't know if that answers your question.
Yeah.
Any other questions? Yes. So going back to large alpha and this time dependence question. So it's very interesting that you had to replace omega, the vacuum, by omega t. But you said that you don't see the change by looking at reduced density matrix for electron, or
yes,
so
not
is there, yeah. Is there any way of seeing this change of omega to omega t through some physical observation?
Well, I mean, you could say we see it here, right? I mean, basically.
Oh, yeah, of course.
We say the wave function is that, right? That's what we're saying. We're computing the wave function up to small corrections in the full L2 norm. So we compute much more than just the reduced density matrices.
Right. So, of course, that I understand.
So you can really see it if you look at the full wave function. And by the way, maybe I should have said, of course, the fact that initially we have the vacuum is then not important. I mean, you have to evolve whatever state you put here according to the fluctuation dynamics, and you have to choose a state that has very few excitations. The vacuum is, of course, the best, but you could take anything, any state that has sort of, for instance, a particle number that's independent of alpha, something that has very few excitations. You see this guy, the Weil operator creates a huge number of excitations, so to say alpha squared. That's why it's sort of superimposed to any other state in the reduced density matrix. You will not see this state at all. That's sort of the statement. You have to look very closely to see it. But if you work with L2 norms on the full Fock space, you actually look close enough to see it. So to say. So you could probably come up with some observable that sees it. I don't know, we didn't think about what observable we have to measure to see it. But basically, okay, so. Yeah,
but anyway, it's very subtle, right?
Yes, I mean, in spirit, it's, I mean, for those in the audience who have worked sort of, for instance, with large bosonic systems, the mean field limit or something of that kind, or also more singular limits, it's a bit the analog of sort of deriving just the nonlinear Schrodinger equation on the level of the reduced density matrices, or really deriving a form for the exact ground state of where you sort of prove that it's equals the one of the Bogoliubov Hamiltonian, right? So you need the Bogoliubov Hamiltonian, need sort of the fluctuation Hamiltonian if you really want to know the wave function. If you're willing to work only with reduced density matrices, it's enough to know sort of the classical leading order term. And that's sort of in spirit, that's the same thing here, except that it's in addition sort of coupled with this adiabatic nature of the evolution, which sort of complicates things quite a bit.
Okay, thank you. Any other questions? Okay, so if not, let's thank Robert for the great talk. Thank you very much.
Thank you.